Good morning, everyone. So sorry that I couldn't be there in person. I really would enjoy it. I recognize the value in the in-person lesson lecture. Shannon and I have to go to Halifax for a last-minute unplanned trip. So unfortunately, I've got to record it. But fortunately, we have the ability to do this and to give you a recorded lecture. So I understand that your studio project is a housing the Yellow Belt, high density, 500 units on the site of a former public school, which is going to remain, um, and and you're going to be exploring a range of possible structural solutions. So we're going to talk about what those solutions might be. Um, um, so what does that mean? So we've got a number of ways that we might build these structures. We would look at light wood frame, which we colloquially refer to as stick frame, for single family housing. That's not what you're doing here. But we can also use stick frame for multi-residential apartments and condos. We can build apartments and condos in concrete. We can use mass timber. We can also use some systems like light steel framing, which is essentially stick framing in steel, um, or concrete and on precast concrete, hollow core on concrete blocks. So there's a wide range that we might tackle this based on the form of the building. For light wood frame, we've said this type of building. For light wood frame buildings, typically we're looking at 2 to 6 stories. The Ontario Building Code has a limit of 6 stories for light wood frame. For years and years, it was 4 stories. They expanded to 6 stories in around 2012. Story to story height is in the 2.4 to 3.2 meter range, and bay sizes for light wood frame are in the 5 to 5.5 meter range. That's the limit for the length of a joist that you can buy in conventional sawn lumber. We're going to look at some sizing guidelines. A sizing guideline is a quick calculation that relates depth to length or depth to span. We often refer to them as depth to span ratios. We'll also talk about width relative to height, but that's a much less reliable sizing guideline. So it's important we do something, but the depth to span ratios are really quite reliable. We do this, we provide you sizing guidelines so that you as the architect can do something that looks reasonable without having to talk to your engineer. So you should be able to draw a building section at 1 to 100 and have things look reasonable. You may not be exactly correct, but it won't be jarring, and it'll allow you to build up your assemblies around it. Okay, some common methods of construction for multi-residential: stick frame or light wood framing, light steel framing, cast in place concrete block hollow core, mass timber. Stick frame up to 6 stories, built using 2x lumber. So a 2x in our air quotes is nominally 2 inches wide. That is, it's actually 2 inches wide, and then it is planed or dressed and winds up being 1.5 inches wide or 38 millimeters. But they call it 2x because it starts off at 2 inches wide. And then the depth varies from nominally 4 inches, which is 3.5 inches, 89, up to nominally 12 inches, which is 11.25 inches, or 286 millimeters deep. Stick frame typically have concrete foundations. There are other foundation systems. We might use block if we don't have a basement. We might use preserved wood. Preserved wood is allowable under the building code, but hasn't really gained traction. I don't think people have confidence in the longevity of a preserved wood foundation yet. Some advantages of stick framing for multi-residential. The material is easily available. As you know, you can simply go to Home Depot and buy your sticks, buy your 2x material. It often doesn't require an engineer's stamp. So stick frame can be designed by the architect as long as you follow a set of prescriptive rules in Part 9 of the Building Code. Very economical. Without a doubt, it's the most economical way to build. Very fast lead time. So there's no prefabricated elements. There's no shop drawings or limited shop drawings that need to be produced and reviewed. It's very fast for erection, so it's a short time on site. Not only is it fast, but winter construction is easy with stick frame. There's a large available workforce, so it's a relatively low barrier of entry for the workforce, and therefore there's a large available workforce. It's got excellent thermal properties. We do worry a lot about cold bridging in stick frame buildings, but in fact, it's what we're trying to do is optimize the envelope performance. But in fact, the heat transfer through wood is really quite good. So we're trying to take something that's already good and make it even better. That's why we worry about cold bridging. Not because cold bridging is terrible. It's not the same as concrete or steel. We have wood treatment options available to us. So like I say, we can use treated wood for exterior decks, for preserved wood foundations and things. And it's corrosion resistant. So we don't have a problem with oxidation of wood, for example. Some disadvantages of wood: it's combustible. Light wood frame is the least fire safe way to build anything. Now, we achieve a level of acceptable fire safety in light wood frame construction, but we do this by protecting the wood with layers of gypsum wallboard, for example, and compartmentalizing our spaces within the building to ensure that we have exiting. But it is combustible. It's very combustible and vulnerable to construction fires. Vibration is a concern. Now, vibration is a concern no matter what we're building with. It's just the mitigation methods with light wood frame are more significant. And if we don't consider it carefully, it is more likely to be a problem. Connections in wood are a problem. Having wood is really extremely strong material, but it's difficult to connect. It's easy to connect if you're bearing. It's hard to connect if you're into the side. It takes lots of fasteners, and there's limited capacities. Member sizes are a disadvantage. So wood construction tends to be a little bit bulkier, certainly bulkier than concrete, comparable to steel in terms of structural depth. So member sizes are a little bit of a challenge. Moisture is a challenge. So not that moisture is a problem. We keep it inside the building envelope, it stays dry, and that's not a problem. But if it does get wet, then the structure can be damaged. So if there's a fire, even if the structure doesn't burn, if the building gets saturated by firefighters, that can lead to having to demolish and reconstruct the building. Also, materials that are outside of the building envelope have a different design life. So we're building a building for 100-year life. If we have an exterior deck, we just have to assume that that's got about a 20-year life, a replacement life. So we don't have the same longevity in all of our materials, or of all our elements within the building. Some sizing guidelines. So these are the standard sizes that are available. I talk about 2x. So you can see the first one, 2x4, is nominally 2 inches wide, which is 1.5 or 38, by nominally 4 inches deep, which is 3.5 inches or 89 millimeters. Joists are the spanning elements that might go wall to wall or wall to beam. We use a rule of thumb of L/16. So take your span, divide by 16. That'll give you the nominal depth of the joist that you might need. And we would typically put joist at 16 inches on center, 400 millimeters on center, about that far apart. The spacing of the joist is determined by what you put on the joist. So if we're putting a layer of 3/4 or 19 millimeter plywood on top of the joist, well, that plywood will span about 16 inches. On the roof, we're not as concerned about it feeling spongy when we walk on it, so we would push that to 24 inches or 600 millimeters. Studs for exterior walls are almost always 5.5 inch 2x6. For interior walls, they typically 2x4 or 3.5 inch studs at 16 inches on center. You'll always be credible if that's what you assume. Beams are a little bit deeper than joists typically. We would actually try to lay out the system to keep everything the same depth, but we would use a depth to span ratio of L/12 to L/14. So generally the beam doesn't span as far as the joist spans. And we can make beams by screwing multiple laminations together. Posts, decent rule of thumb is H/30 for a wood post. So take the height, divide that by 30, that'll give you the nominal dimension of the post. And we can make a post by building it up. So we build it up out of 2x6s or 2x4s or 2x8s. Full size is unusual. So we have 4x4s, 3.5 by 3.5. We have 6x6s. It's rare to use something bigger than that. Plywood, in fact, all panel products, they come in 4x8 sheets. The wood frame industry is still very much imperial. And when we're talking about metric, we're converting an imperial size. So 4x8 sheet, 1220 by 2440 millimeters. And ranges and sizes. By and large, we use 1/2 inch for walls and roofs, 3/4 inch for floors. And occasionally we'll do otherwise, but that's by certainly the standard. We use other panel products as well. So we're using plywood in this lecture as a stand-in for a panel product. What you're seeing in the web of the wood eye joists here is called oriented strand board. So rather than being plies that are peeled off a log, laid flat, glued together, the wood is ground up into chips that are glued together, making oriented strand board. Oriented strand board, or OSB, is actually more common than plywood in construction. It's actually stiffer, so it's a very good material. It doesn't tend to stand up as well to moisture. So people tend to prefer, or often people will prefer plywood, even though the structural behavior of OSB can be better. This product that we're looking at here is called a wood eye, made by a variety of manufacturers in a variety of different ways. This one particular has an OSB for the web and LVL for the cords. Now, LVL is an engineered wood product, and I think we can talk about engineered wood products in a minute, but it's almost like super plywood. So you can see the layers of ply in the top. LVL is extremely strong and extremely stiff, so it's a very high quality wood product that would replace sawn lumber. We can also get wood eyes with solid sawn lumber for the top and bottom cords. So there's a range of possibilities available. Here are our engineered wood products. So on the right is LVL, laminated veneer lumber, which is super plywood. On the left is PSL, parallel strand lumber. And this is glued together similar to OSB, just in a large, more bulky way. Engineered lumber is typically significantly stronger and stiffer than solid sawn lumber. You might wonder why that would be the case. The wood fiber is the same. It's the same wood fiber, just assembled differently. By shredding it and gluing it back together, we end up with a stronger beam. The reason for that is that engineered wood is flawless. You have no knots, you have no checks, you have no wane. Knots, checks, and wanes are all strength reducing features in natural wood that you get rid of by making an engineered wood product. PSL I rarely see anymore. In the early 2000s we saw PSL quite a bit. It's almost been completely taken over by LVL, laminated veneer lumber on the right. There's also LSL, laminated strand lumber, which is similar to LVL, but lighter duty. But again, it looks a lot like OSB, which is oriented strand board. Typical sizing we've talked about, 1/2 inch to 3/4 panel product, plywood or OSB. Joists at 16 inches on center or 400 millimeters. Beams would vary. Beams are often, with light wood frame, we would incorporate steel beams, and walls 2x6 or 2x8 studs or 2x4 studs. 2x4 for interior walls. And here are some images of some larger scale light wood frame buildings. You can see that the perimeter and certain interior walls are up because those are load bearing. These are built in what's called platform construction. So a set of walls go up, a floor goes on top of it. The next set of walls sits on the floor before, which is platform construction. You can see our walls here are OSB. You can tell just looking at them, they have a kind of a sawdust look. In this case, it looks like they're using hollow core precast as the decking material, which is interesting. I don't think I must be mistaken on that. Some framing details, you can see that they're starting to pack in between the studs with insulation. So in our envelope, we insulate the wall cavity, gives us lots of space to put insulation. But you only have insulation between the studs, which makes the stud a thermal bridge. And so we detail our walls to eliminate that cold bridge by adding continuous insulation on the outside. The wall goes up with punched windows. In stick frame construction, the walls carry not only the vertical load but the lateral load. And recall that the lateral load resisting system is what keeps the building from racking. The panel product, the sheathing on the outside, is critical for that. And punched openings are a problem, can be a problem. So we have to design very, very carefully to make sure that there are not too many windows and the windows aren't too big to affect the wall's ability to resist lateral loads. I want to point out, you have probably seen examples where this is not the case, but you can see that all the buildings, the balconies are completely wrapped. And you might wonder why. It's not a thermal separation, and yet they've completely wrapped the building with the balcony. And the reason is, as I mentioned before, that wood in an exterior environment, even if it's pressure treated, has a 15-20 year life. And we're designing buildings, if we're doing it right, we want a building to have a 100 to 200 year life. And so we've got to protect those elements. So you can see we can wind up with some very large buildings in light wood frame. This is light steel frame. And you can see that it looks very much like light wood frame, except that the elements are silver instead of amber color. One difference is you can see there is no sheathing in light wood frame. So in light wood frame, the sheathing, the panel product on the outside, is not what's carrying the lateral loads. You can see a bunch of X's on the walls. Those X's are steel straps on the outside face that get screwed to the studs. And those straps act like X bracing in our building. Okay, now we're going to talk about concrete. So, because concrete, in all likelihood, is probably what you're going to do. I think there's a slide on this afterwards, but when we are choosing our structural system, it is highly unlikely that we can invent something that is better than the evolution of design decision that's been made over hundreds and hundreds of buildings. And so looking at the precedent, if there is a well-established archetype for a building, that is probably the most efficient way to build it, notwithstanding the very clear and obvious sustainability problems we have with concrete, but we can talk about that. So by and large, the great majority of multi-residential buildings are built in concrete. The reason they're built in concrete is because it is the most effective way to build them. And as much as we want to build as much as possible in wood and mass timber, we will never replace all of the concrete buildings. So solving the concrete building sustainable concrete buildings is actually a really important problem to solve. So concrete apartments and condos. Typically, multi-residential is cast in place concrete. The form is erected, rebar is placed on top of the form, concrete is placed on top of that. The concrete cures as soon as it's self-supporting. The form is demolished underneath. And Barry Sampson, who most of you will not have had an opportunity to meet, but he was so integral to the Daniels faculty for so many years, he always said that a concrete building is a building you build twice. You build it once in wood, and that's the formwork. You pour the concrete on it, and you've got a concrete building, and then you demolish the wood building that you had to build to build the concrete building. Foundations are typically cast in place concrete. We consolidate materials if we can. So what are some advantages to concrete? It's easily adaptable. So we can adapt it to different forms, different building sizes. We can incorporate long spans, short spans. Has a short lead time, not a lot of prefabricated elements. So rebar has to be cut, it has to be bent in advance, but that's a very quick process. Shallow depth of structure. This is really important when we're building tall, because the deeper the structure, the higher the floor-to-floor heights. The higher the floor-to-floor heights, the fewer floors you can build, for one thing. But also you build an extra 50 millimeters. If the structure is 50 millimeters deeper, that's 50 millimeters of additional wall all the way around the building. It's 50 millimeters additional per floor of additional surface for the wind to blow on. So the loads are bigger. So floor-to-floor height is actually a really important thing. And concrete has a shallow depth of structure. Ironically, the reason concrete is shallow is because it's weak, which is exactly counterintuitive. Because being deeper makes the system stronger, and one would assume that a deeper material or a weaker material you need to go stronger. But in fact, a weaker material needs to be more robust. You need more material, and if you need more material, it can afford to be shallower, because it's governed by vibration and sag as opposed to by bending strength. So you cannot follow that logic without actually working out some numbers, but just understand that weaker materials generally can be shallower. Stronger materials to get full utilization of them often have to be deeper. They're lighter. Stronger materials make things lighter, but they have to be deeper. Concrete has an advantage to finishes. So when you build a concrete structure, you can expose the underside, and your ceiling can be exposed concrete. It's non-combustible, so unlike the light wood frame, it's inherently fire safe, and has a good fire rating. So those sound like the same thing, but they're not. Non-combustible means that it doesn't contribute fuel to the fire. Good fire rating means that it will stand there for a duration, allowing people to escape the building. Wood is combustible. It contributes fuel to the fire. Wood can also have a good fire rating, and allow people to escape the building. So the two are not the same. Concrete is very good acoustically. So from a sound transfer rating, an STC rating, it's excellent. So airborne noise is blocked by concrete very well, better than other materials. Impact noise, you still got to be concerned about, but concrete is ductile. It's a very strange statement because concrete is actually extremely brittle, but reinforced concrete can be very ductile. The ductility coming from the yielding of the rebar, and ductility is extremely important in a seismic environment. Concrete is corrosion resistant. Another strange statement because we've all driven down the Gardner and you see concrete falling off the beds, or you go into an old parking garage and you see that it's dilapidated. It looks like it's falling apart because of the corroded rebar. That's true. The reason we see corroded concrete structures is because they build concrete structures in corrosive environments because concrete is the best. So it's the best, so they put it in the worst environments, and so we have this perception that it's corroded, that it corrodes. But in fact, it stands up to the environment very well, but not perfect, but very well. Disadvantages in concrete: it's heavy. So that's the last thing on my list here, but in fact it's the first thing. The biggest job concrete does in a structure is carry its own weight, and so concrete is heavy. The heaviness means a number of things. One is in the seismic event, the magnitude of the lateral seismic forces is proportional to the weight of the structure. So the heavier the structure, the bigger the seismic forces. That's not a good thing. Also, the longer the span, the deeper the structure, the heavier it gets. So there's this feedback loop with concrete because it's heavy, that really limits the length of span. So we don't do long spans in concrete. Concrete is a little hard to alter because you can't go put more rebar in a slab. Once the slab is poured, it's poured, that's it. So alteration it's not impossible, but you're into adding beams and putting straps on it. It's complicated to alter. Construction is sensitive to weather. Concrete, if it freezes prior to curing, it's no good. Or if it freezes too early and forms ice within the concrete, that can severely impact the concrete strength. If it's allowed to cure to a certain point and then freeze, it may ultimately attain all its strength, but the strength gain is severely delayed. So concrete is problematic. Also, concrete is built in the field. Steel is built in the shop and assembled in the field. Concrete is fabricated in the field, and so people are working outside in the elements, which means that quality control is a challenge. Other disadvantage: very high global warming potential. That should be right here in the slide. So the embodied carbon in concrete is extremely high. The cement production alone is responsible for 8% of greenhouse gases worldwide. There is a worldwide sand shortage. Only sand, I don't know what they call it, water sand. Only sand that is harvested from the bottom of a body of water can be used for concrete. Airborne sand gets polished too smooth, so desert sand can't be used. And we are destroying beaches and rivers all over the world, riverbeds, destroying habitat by harvesting or mining sand for concrete construction. Okay, let's look at some sizing guidelines. Precast hollow core slab. So you can see these slabs, they've got holes down the middle. The reason why they have holes down the middle is because the middle of the concrete's not really doing very much for you. From a bending point of view, all the work is done in the top and the bottom. And the middle's not helping. From a shear transfer point of view, you need concrete in the middle, but its utilization is very low. So you don't need all of it. So you need, maybe a quarter of the concrete to transfer the shear. And so hollow core precast is an ingenious response to that. Takes all of the concrete out of the middle, which makes it substantially lighter. Manufactured off site, so erection is quick. So hollow core is an ingenious product. Major disadvantages with hollow core. One is floor flatness. It's it's pre-stressed, so the tendons are put in tension. The concrete is placed as the concrete is cured before the tendons are released. That means that the panel is, the concrete in the panel is in compression. That's wonderful from a spanning point of view because we take the tension out. The concrete doesn't crack. If it doesn't crack, it's stiffer. There are tremendous benefits to that. But it means that they tend to bow due to the pre-stress. So floor flatness can be a problem. Diaphragm action can be a problem. The diaphragm is what keeps your building square and plan. Just like the shear walls keep it square in elevation, the diaphragm keeps it square in plan. And if we break up our diaphragm into panels, that's a challenge. It's a challenge that can be overcome, but it's a challenge. So we can't take it for granted. But the single biggest problem in my mind with hollow core precast is that even though you are reducing the concrete quantity, the global warming potential of the concrete you're using is going up, and it goes up fast. So you've taken 50% of the concrete out, but your global warming potential of the concrete you're using is double. So it's comparable to a solid slab. And the reason is they need this concrete to cure fast. And if you want concrete to cure fast, the way to do that is use more cement. And cement is the constituent element in concrete that has the most global warming potential. Made and engineered by the fabricator, it comes nominally in 2-inch increments from 8 to 14 inches, or 200 to 350 millimeters. Depth to span ratio, L/40, so very shallow. It's the shallowest of our structural systems. Typical use, things like motels, hollow core precast on concrete block walls, terrific for kind of low rise, non-combustible construction. We've also used it frequently. Goldring Athletic Center, hollow core precast. Robarts Library Edition, hollow core precast. Some cast in place sizing. So one-way slabs, something around L/18. So a one-way slab is a slab that has a dominant strong direction with walls or beams and the slab spanning the other direction. And so roughly L/18 is a decent rule of thumb. Two-way slabs span simultaneously to beams in one direction and beams in the other direction. So they span two directions at once because we can have rebar going both ways. So unlike stick frame, concrete can span two ways at once. Where stick frame, you have deck goes this way, joist goes this way, beam goes this way, girder goes that way. They have to stack or in orthogonal layers. And so two-way slabs, we can go significantly shallower. L over 30 is a common depth to span ratio. Some beam sizing guidelines. We don't have flat slabs and flat plates in here, actually. So a flat slab, or at least I'm going to advance here a second. No. So back up here. Flat slab is a slab that has drop panels around the columns. So it's uniform thickness, but around the column, covering roughly 10% of the area, are thickened zones around the column is a flat slab. Flat slab we would generally use around L over 30. Flat plate is a featureless soffit, and completely smooth without thickened areas at all. We would still probably use L over 30, maybe a little bit deeper, but we are limited in span with flat plate to something around 6 meters. Some beam sizing guidelines. Little image on the left is what a concrete beam looks like in section. And we're generally talking about L over 16 to L over 12. Concrete walls and columns. A wall would be the height divided by 20. Is fairly common. And you can see like 150 millimeter thick wall then can be 3 meters tall. So they're fairly slender. And concrete walls, H over 25. Again, these rules of thumb, we would not design using these rules of thumb. These rules of thumb are good for making sure your 1 to 50 building section looks reasonable. Some masonry sizing guidelines. Load-bearing partitions, H over 20, so very similar to concrete, a little bit thicker. And non-load-bearing partitions, H over 36. That's an interesting one. 100 millimeter thick, 3.6 meters tall. Very, very slender for non-load-bearing partitions. So concrete condos, what is typical? So typical sizes for floors, 200 to 300 millimeters thick. I would say that 99% of condos are built with 200 millimeter thick slabs. It is far and away the most common. Walls, very commonly 200 millimeters thick, but can get much thicker. We can have a core wall around an elevator in a tower that might be 0.5 meter thick or 600 millimeters thick. They get very thick because they're working extremely hard. Beams in condos, we would typically only use beams where we need transfers. So, a very common condition for a multi-residential building is 6 meter spans for the tower, but below grade parking, and below grade parking 6 meter bay size just doesn't work for us. It's not effective. And so below grade we would go to 9 meter bays, and then we would have a transfer level at grade to negotiate between the 6 meter bay above and the 9 meter bay below. We want to minimize transfers. Transfers are something we strive to avoid because they're expensive, but we put them in where we need them. Some images of cast in place concrete in construction. So this is below grade. You've got perimeter concrete walls. The ground floor slab hasn't been poured yet. All the rebar in place and concrete being poured from that giant bucket. What you're seeing here is called flying forms. So if you look at the top level, the yellow beams that are sticking out, that's a form table. That form table will be dropped, pulled out of the bay, and then put on top of the slab that has just been poured, and to be ready to pour the next slab up above. So the forms are reused. Um, because of that, concrete gains its efficiency at 4 stories or more, because you're reusing your forms. Building only 1 story in concrete, you only get to, like, you build and you demolish that wood building once, and you don't get any efficiency from reuse. Um, the tiny little posts you see in the bays where you don't have forms, you see tiny little posts. Those are called reshores. The forms are stripped before the concrete has full strength. So we take the forms out, we put a reshore in, we put a shoring jack in, which will just alleviate the load on the concrete until it comes to full strength. The other thing the reshore does is shares load from floor to floor to floor, because the top level we're pouring concrete, the weight of that concrete may be more than the slab was designed for. The slab below was designed for. It's not designed to carry its own weight plus live load plus the weight of concrete of the next floor. So we share that load over multiple floors down below using reshores. Talking about the global warming potential of concrete. So it's an extremely important way to build, and yet it's a very high global warming potential. One of the solutions that we employ to mitigate that is voiding systems. So just like the hollow core precast had those continuous voids through it, we could put voiding balls in cast in place concrete that do exactly the same thing. They just displace concrete in the middle where it's not doing anything for us. It's not contributing strength, but it is contributing weight, and it is embodying carbon. So we cast these balls into the slab. And the Daniels building was built using bubble deck. This isn't an image of Daniels, but it would have been very similar. The reason the balls are multicolored is because they're made with recycled HDPE plastic. You've seen the kayaks at Canadian Tire. They're made of HDPE plastic. When a kayak is rejected due to a manufacturing defect, the plastic gets ground up and they use it to make balls for the whole deck. Bubble deck has historically been a thick slab solution. You can imagine that the thinner the slab, the smaller the balls get. The smaller the balls get, the more balls you need. And the mesh that you see is what holds the balls in place and keeps from migrating around. The smaller the ball, the denser the mesh. So the cost of bubble deck goes up as balls get small, as slabs get thin. So it's typically been a thick slab solution. We've been working with bubble deck to develop a thin slab solution because we just recognize how critically important it is to be able to void the concrete in thin slabs. I heard a statistic which is probably not true, but it's true enough that I will repeat it and we will establish it as fact. That 50% of all the concrete in the world is poured in elevated slabs for residential buildings. So solving this problem is a tremendous benefit. The voided concrete system will take roughly 25 to 30% of the concrete out of a suspended slab. So you can imagine that is a huge reduction in global warming potential. And then we can look at low carbon concrete. So the simplest way to build low carbon concrete is to use low carbon alternatives to Portland cement. So Portland cement is made by heating up limestone to an absurdly high temperature, and then powdering it so that it becomes very, very fine powders. But it's extremely energy intensive, Historically, it's been done in coal-fired furnaces, which also certainly is really problematic. Um, we can supplement some portion of the cement with fly ash. So fly ash is a waste byproduct of coal-fired generating plants that's captured from the exhaust stacks. So that fly ash can be used as a supplementary cementing material that is carbon neutral. Um, we are doing away with coal-fired generating plants, of course, and so fly ash is not a resource that is readily available, and hopefully it will not ever be available. But another one we can use is blast furnace slag. So this is a waste byproduct of the manufacturing of steel, and that's fairly commonly available. So we are commonly asking for blast furnace slag to supplement and substitute some of the cement. And using relatively easy techniques, we can reduce the global warming potential of the concrete by something like 15%. There are other ways of building low carbon concrete too. Of course, there's carbon capture, techniques like carbon cure, for example, that actually capture and store some of the CO2 in the concrete. There are methods of making Portland cement that do not require heat. So these are kind of experimental, or in early days, so it's not readily available, but we're getting there. So we're migrating towards carbon neutral concrete. But right now, right off the bat, we can dramatically reduce our global warming potential of concrete by voiding out the concrete that we don't need, and by supplementing the cement to the extent possible. One of the things we need to do, so concrete strength is a function of how much cement you put in it. And the less cement, the weaker the concrete is. If we don't need strong concrete, we shouldn't use strong concrete. We should be using the weakest concrete that achieves our goals. The other thing we need to think about is rate of strength gain. So if we want concrete that is 30 MPa at 7 days, then what we need to do is we need 50 MPa concrete, because it'll be 30 MPa at 7 days. If we can wait 28 days for it to achieve 30 MPa, then we can use much less cement. So thinking about construction techniques that do not need an accelerated timeline. Of course, I mean, concrete, what we want to do is build fast. Like one of the problems with concrete is the time it takes. So that's a competing objective. How do we build fast without using too much cement? So here are some images. So concrete can be left exposed to view. That's an aesthetic. Not everybody wants that aesthetic, but it can be left exposed to view in the finished building because it is non-combustible, fire safe. And so it's actually fairly commonly left exposed to view, both on ceilings and on floors. Now, we talked about STC rating, that's sound transfer rating, terrific, no problem here. But impact noise, this is don't remember what rating that's called. This is problematic for impact noise. So somebody drops a glass, the person down below is going to hear it as though it was in their own kitchen. Some concrete condos. I'm just going to point out the balcony. So concrete buildings with balconies are like the radiators on old motorcycles. You remember old motorcycles? You'd look at the engine block, it had all these fins on it. Those are cooling fins. The explicit purpose of those is to lose heat from the engine. The balconies on concrete condominiums are a bit like radiating fins, intended to lose heat. So we have two things that we can do. We can wrap them in insulation, not great from a durability point of view. It's also not cost effective. Number two is we can introduce thermal breaks. So we can put a thermal break where the balcony meets the building envelope. If we can put a thermal break there, great. Trouble is there's only one commercially available thermal break that I'm aware of, the shock thermal break, and it's very expensive. So there's that's a problem that we need to solve as a building industry is effective, cost-effective, simple thermal break techniques. One thing we do frequently is we just put a slot. So make sure that you only have just as much concrete crossing the envelope as you need for structural performance, and that's a benefit. We also see some examples with bolt-on balconies, which can be thermally broken. So bolt-on steel balconies instead. Okay, that's cast-in-place concrete. Let's look at mass timber apartments and condos. There's fairly little precedent. The precedent that exists within the limitations of the building code are limited to 6 stories. The most recent, I think 2022 National Building Code allows 12 stories encapsulated mass timber. That has not been adopted in Ontario yet, but it's a matter of time. Large municipalities like City of Toronto have, the building code has alternative solution provisions that if you can demonstrate that a system meets the intent of the building code, whether or not it prescriptively meets the building code, then it is permitted. But you have to demonstrate that it meets the intent. But because of that, we're building the Academic Wood Tower in U of T, which is 14 stories and 77 meters high. So goes well beyond the prescriptive limits of the building code. So we can build larger mass timber buildings, but we need to do it using an alternative solution provision. But 12-story encapsulated mass timber is permitted under the National Building Code. The IBC in the US will permit 18-story encapsulated mass timber. And why that matters to us is if we're doing an alternative solution, we can look to the research that was the basis for that code change and use that as evidence to support our alternative solution. So it's not permitted in the building code, but we shouldn't shy away from it. Mass timber, just to remind you, so mass timber, because I know that you've seen lectures on mass timber before, probably by me, but mass timber is characterized by large flat planes without projecting elements to the extent possible. Massive elements, so minimum element size is like 89 millimeters or something, and there are explicit definitions, and there's a link to a lecture that gives you more detail on this. And then the other thing about mass timber is that we have these massive elements that are manufactured by gluing together solid sawn lumber. So a glue-lam beam is solid sawn lumber stacked and glued together to make a big beam. Cross-laminated timber is solid sawn lumber this way, glued to a layer this way, glued to a layer this way, like super plywood. So mass timber is massive and free of projections. So we can't have a whole series of beams close together. That doesn't meet the intent of mass timber. What we need is big flat surfaces. The reason we need big flat surfaces is that wood will self-extinguish on a big flat surface. That wood only burns in the presence of external fuel source if you have big flat surfaces. If you have a bunch of joists together, it creates a re-radiating zone and then it will burn, but a big flat surface won't. And anybody who's tried to light a campfire knows that that's true. Wood can be the finish, which is a tremendous benefit. It is acoustically reflective, like concrete is. So if acoustics are a concern, you wind up covering portions of it. Wood is lightweight, which means that sound transfer is a problem where it isn't for concrete, and often we'll end up putting concrete toppings on for acoustic reasons. We typically use concrete foundations, mass timber. So some advantages of mass timber construction. It's fast to erect. So we prefabricate the elements in the shop to a high level of accuracy and precision, and then it's only erected in the field. So it's fast. Carbon encapsulation. Now, general carbon I think encapsulation is not the right word. Sorry. But it's the general carbon accounting principles do not allow us to take advantage of the fact that we're capturing carbon within the wood, because at the end of building life, that carbon winds up back in the environment. So we're only capturing it for a certain period of time. But the fact is that all the wood in the built environment is captured, and as long as we preserve that amount of wood in the built environment, it's captured forever. So as long as we're building buildings as we're demolishing them, then the amount in the built environment is captured forever. If the amount of carbon in the built environment is increasing, or if the amount of wood is in the built environment is increasing, then even as we're demolishing buildings, we're building more buildings than we're demolishing, and we are having a net positive permanent carbon capture. So we can't count it in our carbon accounting, but it is doing good. We can use wood as finishes. Excellent thermal properties. So wood is far less thermally conductive than concrete or steel. And so even if wood presents a cold bridge, the amount of energy loss through that cold bridge is dramatically less than the other materials. Mass timber has treatment options, so we can expose it. Generally, we don't. We keep it inside the envelope. It's corrosion resistant and fire resistant. I talked about the fire burning characteristics of mass timber a minute ago. Disadvantages: lead time. These projects have to be meticulously planned and fabricated in the shop. So there is a long lead time for mass timber. It is combustible. Now, combustible does not mean that it's not fire safe. It just can contribute fuel to the fire, which puts limits on the size of the building that we can build. It's lighter weight, which means we have to actively mitigate vibration. Connections are a challenge. They're not a problem. They're a challenge. They're just more difficult in mass timber because wood is harder to connect. And connections, if they're made of steel, we need to fire protect them. So, there's this kind of careful dance of how do you have a robust connection and still be fire protected. Member sizes are a challenge. So if we look at 80 Atlantic, which is a wonderful building, the first commercial mass timber building built in construction in Toronto in 100 years. The pro forma for the building was to have a building with 9-meter spans and 6 stories tall. What they built was a building that had 6-meter spans and 5 meters tall. And that was all about member sizes in mass timber. They just get big. And then moisture protection. Moisture protection, permanent, which can lead to decay, but also temporary. We need to keep the wood from getting saturated during construction, and that can be a challenge. So some sizing guidelines, beams L/14, or engineered beams L/16. So solid sawn versus engineered lumber like glulam. Engineered can be a little bit shallower. Posts and columns are similar to sawn lumber, and proportions D/2 to D/3. So the typically the width is half to a third of the depth. CLT comes 2 feet to 10 feet wide, up to 60 feet long, up to 20 inches thick. Now, we say 20 inches thick. 9 1/4, anything bigger than 9 1/4 inches or 7 plies is uncommon. 11 plies is possible, manufactured in Canada, I believe, but very uncommon. More than that is really it would be a very bespoke application, and it would be hard to find somebody willing to do it. So technically possible up to 20 inches thick, but 11 plies of 35 millimeter is really an upper bound. 9 plies is a practical upper bound, and we try and stay at a 7 ply, 5 and 7 ply. Typical sizes, we try to stay to 5 ply, 7 where we need be. We provide beams where we need transfer, so lobbies, for example. Typically, we would have cast in place concrete for the parking area from a durability point of view, and then we would use mass timber for the building up above. That's not necessarily the case. You can build parking in mass timber, and they're doing one at U of T Scarborough, or maybe it's Mississauga, but one of the U of T campuses is building a mass timber parking garage. Here's some mass timber construction images. Big panels getting screwed together, typically held together with large, long screws. Going up very fast. It's very quiet, very warm, mass timber construction. So it's ideally suited to a cold climate. And it's warm because you don't have radiant cooling problems with mass timber. You know, if you're walking in a concrete building on a 20 below day and all the concrete is 20 below, you actually feel cold radiating off the concrete. No, that's not actually what's happening, of course, because you don't radiate cold, you radiate heat. But concrete will absorb the heat radiated off your body, where wood will reflect it back to you, and it feels like the wood or the concrete is radiating cold. The erection process of mass timber, dropping in a CLT panel onto our mass timber beams, and a completed project. You can see the balcony, actually. You can see the underside of the balcony is exposed mass timber. It's because it's not such a problem, the thermal break. We do thermally break mass timber to the extent we can, but the fact is that the material we use as a thermal break in steel or concrete is twice as thermally conductive as wood. So it makes it a real challenge to thermally break wood when thermal break material is actually more conductive than the material you're thermally breaking. So long spans. When we get into long spans, we're typically using structural steel, and we can hybridize structural steel with mass timber. Concrete, we hybridize less with steel, but we do with concrete as well. Long spans and mass timber. We have big members, 9 meters or 12 meter spans is possible. We try and stay under 12 meters because 12 meters is a standard truck bed, but the fact is there's no problem getting an 18 meter long beam and getting it to a site. You know, where the length of element is less critical than the width from a shipping point of view. Concrete, we can do long spans if we are prepared to post tension the concrete. So when do we mix materials? What we try to do is not have multiple trades on a site at the same time. So if we're mixing concrete and mass timber, we try and do the concrete up to a podium level and mass timber up above, for example. The building that I'm in, 134 Peter Street, the new construction started 8 stories up in the air. That was a steel table because it was much simpler to build steel floating up in the air above the big delta frames, and then concrete above that. But they try to be discreet and not have 2 trades working at the same time. Hybridizing mass timber and steel is extremely common. The academic wood tower, our central core is steel. That was a major concession in order to get the tall building, is that the core had to be non-combustible. So the core is steel, wood around it. Limberlost place is the same. When we get into tall buildings, we would often use steel columns or concrete columns as opposed to mass timber columns, just because mass timber columns get really massive. They start eating up a lot of real estate. How do we choose our system? Well, I think I mentioned that the first thing you do is you look at the precedent, and probably if there is a well-established archetype, that is the most efficient way to build it. And so we start by understanding that, and then we elaborate, we refine that system to suit, and we innovate or deviate when we need to. So that's the end of this lecture. I'm just going to flip through here and show you what else is in here, because this PowerPoint is available to you. I wrote an article for the Canadian Architect, the Mass Timber Primer, so feel free to go back and look at that. The world is changing rapidly, so even though this article is only a few years old, there are things that are slightly out of date, but it's still a decent starting place. And there's also a mass timber lecture that you can watch on YouTube that Shannon and I gave. And then also within this, these are a bunch of slides of mass timber systems that we incorporated in the lecture. So we've incorporated them in this slideshow so that you have them to refer to at your fingertips. But if you watch the lecture, you'll see the context associated with all of these slides and the background. So that's the end of it. Again, I'm very sorry that I couldn't be there in person. I definitely enjoy coming in person and look forward to meeting those of you who I didn't meet in CRITS at some point. And best of luck with the evolution of your project. Okay, bye, gang. Have a great day.